very good perception. I'm actually pretty sure this is where I am right now. But in certain cases, you might not be sure which state you end up at. So in that, we also have some probability distribution. So this says, like, if you're in state S0 and you take action A0, there's about a 50% chance you're going to end up back in state 0. And there's a 50% chance you're going to transition successfully to state 2. Right? And this is basically it. So if you compare all of this to your standard state machine, the only difference is that at every state you've got a choice. And that choice is represented by these actions. And every action is non-deterministic, which means that you don't actually know which state, with certainty, which state you're going to end up at. There's probably like some probability distribution on as to which state you're going to end up at, right? That's basically it. So here's a quick teaser. Like I don't know if anybody is expecting you're going to have to do this, but you are, and I'm going to wait 2 minutes for this. If this is the state machine, and I know this looks really, really bad, you can see this nice +5 reward over here. What's the best policy for the state machine? And a policy is like, what action do you want to take given a particular state? So given, if you were in S0, what action would you like to take to maximize your overall reward of the system? If you're in S2, what action you'd like to take? And if you're in S1, what action you'd like to take? And if I'll give you about 2 minutes to figure out which action is better for every state. Random chance will get you 50% of the way there, so you have to do better than 50% overall, and figure out how well we're doing. Or I'll give about 30 seconds more and then we'll discuss this after. All right, everybody has some idea as to what actions they'd like to take in each state. Just to recap, policy is basically a mapping from states to actions. So for every given state, you have to select an action. An optimal policy is that maximizes the overall reward the system's going to receive, so you can keep on getting nice rewards as you go along. And we can compute the optimal policy. So there's actually a closed form solution. Well, it's not exactly a closed form solution, it's an iterative solution, but there is a solution to this that if you keep doing this over and over again, we can actually calculate out theoretically which is the best action at every state. All right, so coming back, if to look at this, let me go back to this first. So I think I'm correct because I actually don't have the, I just remember this off the top of my head, but like, so for state 0, how many people pick A0? And how many people pick A1? All right, awesome. State 2, A0, A1. All right, and state 1, A for A0. Okay, so I think that was most hands. So okay, all of you got it right. That's good. So now you can go ahead and confidently say that you have some idea about Markov decision processes. There's a bit more to it than what I've explained here, but not that much more. As long as you can relate it to something you're probably fine. So just to give you an idea, when we have this nasty looking equation here, you don't you look at the math and it looks scary, but it's not really. It's all it's saying is that I'm going to try and solve this over multiple iterations. So initially I'm going to assign a value to every state as to how much I think that state is worth. and that's called the value of that state. And what I'm going to try and do is I'm going to try and update these values based on how you move from one state to another state. And once the values converge to some fixed value, then I have a very, very good understanding of, what's the best policy on each state. It's how you maximize, how can I maximize this value. So all of this is saying is that if you are in a given state, you have the probabilities of transitioning to all the next states given you select a particular action. You'll get a reward for that transition, and there'll be the value of the next state that you might transition to. So for instance, let's take a look over here. So if you've got this S0, I have two actions over here, so that max is over two actions, A0 and A1. And what we'll have is, if you select A0, there's a probability of transitioning to S0, which is 0.5. So this one, for the first time over the loop, is 0.5, and the next time it's also going to be 0.5. And then you see the reward. The rewards are in these cases 0, and then you take the value of the state that you end up at, which is going to be 0 initially, because that's what we assumed all the values were. So you start at all zeros, you run this a bunch of times, and then you end up with good values, and then you just select the action that maximizes this value, and that's how you get your policy for each state. If you do this value computation, I think it converges about by the 10th or 5th or 10th iteration, something like that, and these are what the values come out to be. And this is basically saying that being in state 1 is really, really good, because I know that if I take this action A0, I can get to the state S0, which gives me a +5 reward, right? So that's really, really nice. It also knows that if A0 fails, I'll get to S2, and from S2 I can get back to S1. So this is really nice because it's taking this whole loop into account as well before calculating the final value out. So that's why it's nice, because it's a really nice solution to this particular problem, right? Any questions so far about MDPs? So this is like the really short primer on it. Feel free to read it up. I think Wikipedia's got a pretty nice explanation, but there are a couple of really nice online links that take it step by step, and which are pretty good if you're ever interested. Okay, so coming back to our whole multi-robot guidance thing, what we simply did was we modeled it as a Markov decision process, and now I'm going to be a little fuzzy with the details, but that's fine. The details are somewhere, so you can always look them up if you're interested. But the idea is that these pieces of information were all part of my state, right? Like my state is defined by things like where the human is, where the goal is, what does the environment look like, so all those sort of things are part of the state information. How a person actually behaves when I tell my system to direct that person over there is part of this transition system or probability distribution. Right? There is some chance that the person might transition over there, there's some chance that the person might transition over there. So those are two separate states, and that's the probability function, probability distribution I just mentioned. And this one over here are the actions the system can take, placing robots or directing people. And that's basically it. I'm going to skim over some of these details. I've got slightly more detailed slides about the state and the state representation and the Markov decision process in general, but that's we can skim over some of these details. This is basically, you need to have an idea of the human's current location, which direction the human has moved in, because if I've moved this way and I don't see a robot over here, I'm more likely going to continue moving that way. So you have to keep track of certain state variables to figure out where the human is going to go. And if a person sees a robot, then they're likely to move towards that robot. That's a pretty obvious one. And similarly, if I come across to here and there's a robot here telling me to go that direction, so that's also a state where I'm more likely to go over there than over there, and so on. So all of these features you need to keep track in your state, and the system can take these actions, which are it can place a robot, it can direct a human when the human reaches a robot, or it can do nothing. And between these three actions, you can cover every possible scenario, and let the human walk around and figure out the best way to the goal. The last thing is the actual human motion model itself. To have this human motion model, we need to have an understanding of how humans are going to behave when we have a robot guiding them in a particular direction. Now, obviously, we need to have some studies that have been conducted onto this. We hadn't conducted the studies at the time, so we hand-coded this up, which is nice to do. So we made up a bunch of numbers and said that this is probably how a human's going to behave. Now that's fine, except now we actually have to go back and look at those numbers, probably do some studies to say that those numbers are actually valid. All right, so that's basically it. Oh, and more importantly, the reward, right? So in the MDP example I showed you, the reward was like arbitrarily defined. There's a +5 over there, there's a -1 over here. Since we want to minimize the distance the human travels, all we have to do is take the distance, the Euclidean distance from one graph node to another graph node, and set that as the negative of the reward. So it means that if we don't have a system where we get the human to the goal early, we are going to keep on receiving this negative reward over and over and over again. So if we try formulate this as a Markov decision process, set this as the reward, the optimal solution that the Markov decision process provides is actually the one that's going to minimize the distance the human is going to walk in the environment. So that's basically the trick that you have to use. Right, and the equation I showed you for solving this Markov decision process was called value iteration. And you run this like for the example I had there, I wrote everything up in a script and it ran for like 5 iterations and managed to solve the Markov decision process. Since this is a far more complicated MDP with probably like 50,000 states or something like that, it means that it takes it about 5 or 10 minutes to solve the MDP, but it does do so. We've also got a few tricks in there to make the solving time faster. But what this means is that, given a map of the environment, I can pre-compute this best policy. And as a human is walking around the environment, I just need to look up this policy. So I don't need to spend 30 minutes every time